That is my signature tune. Good evening, everybody, and welcome to this sort of open session, I think we'd call it, discussion session about the extraordinary pictures we've been seeing over the past couple of days from the Webb Space Telescope. Tonight's going to be very, very informal. What we're going to do is, I've got some experts here, and I'm going to ask them to introduce themselves. To let you know who they are and where they come from and why they're here. And we're then going to start looking through some of those pictures, and I'm going to ask the panel to comment on it and tell us a bit about it. But all the time I'm looking for questions from the audience and online. If you have particular questions about that particular image or about the observatory and so on that you want to ask. So it's very, very informal. We'll just chog our way through the pictures and talk about them. Hopefully it won't get too boring. And so I'm going to introduce the panel quickly, and I'll start on my left. Perhaps you can introduce yourself.
Yeah. Hi, everyone. Good evening. My name is Piyal Samara-Ratna. I'm from the University of Leicester. And we have a responsibility for the engineering. So I'm not here really to talk about the science stuff. That's for the experts here. But really, I was lucky enough to be a mechanical engineer as part of the lead mechanical engineering team on the MIRI instrument. And so I had a leading role in delivering the instrument to NASA, putting it on spacecraft, supporting the testing, working with an international team. So.
Thanks, great. So let's go outwards that way and then we'll come back along this way.
Oh, okay, sorry, was it supposed to be me first? I apologize. My name is Dr. Becky Smethurst, and I am an astrophysicist at the University of Oxford. My research specializes in supermassive black holes and how they affect galaxies. And I was very, very excited to see the galaxies image, especially yesterday. It's stolen my heart already.
I'm Steve Wilkins. I'm head of astronomy at the University of Sussex. And I study galaxy evolution and formation. In particular, I try and look for the most distant galaxies in the universe. So I was really, really excited on Monday when we got that first image, because that's the one that I really care about in terms of science. And already just this afternoon, we were downloading the image and trying to find those galaxies. So what I'm really hoping to do is actually find examples of the very first stars to form in the universe.
Okay, and on the end.
Hi everyone, I'm Olivia Jones. I'm a member of the MIRI commissioning team, so I've been working in Baltimore in the last month or so, getting these images, well, not the final images, but some of the calibration ready for the data that's coming out today and tomorrow. I'm also a scientist. I work on anything dusty in the universe, so the infrared is my very happy place, but mostly evolving young stars in nearby galaxies.
Hello everyone, my name is Eva-Maria Ahrer. I'm from the University of Warwick, so this is my home university here. So I'm part of the early release science transiting exoplanet communities. So I study exoplanet atmospheres, and so I'm very excited about the spectrum we saw yesterday, and we'll talk about more later about this.
Okay, thank you very much. Now, perhaps I think most people will know this, but I'm just going to try and see if we can just summarize things for those of you who don't really know a lot about the telescope and so on. See, correct me if I'm wrong, because I probably am. I'm Mike Edmunds, by the way. I'm the president of the Royal Astronomical Society and therefore know very little. This project has been, going for about 20, 25 years or longer?
1995.
1995, okay, so that's, yeah, about
20 odd.
to astrophysical accuracy, okay. The primary mirror is what diameter? 3.5 meters?
No,
6.5.
6.5. There's been quite a lot of inflation since 1995. 6.5, of course it is. And it's a folded, as you know, it's hexagonal, it's all folded up and whatever. The launch was very successful, somewhat delayed, we have to say. We've been waiting for this for some years. But very successful, extraordinarily successful, really. And I gather there's delightful news that the telescope could operate for 20 years. Is that right? They've got enough fuel on board that it could operate for 20 years, which is tremendously exciting if you think about it, that quality of observatory is going to be around for that length of time. And really, I suppose that's all we need to know about it. Particularly, now, can you give me the wavelength region again? It goes from
600 nanometers to 26 micrometers.
Okay.
For all those that means something to in the audience.
So that's red, far red, very red light. Yeah, on one end, right out into the sort of mid-infrared. Would that be true?
Yeah.
Yeah. Okay. And we've had nothing really like that. Not with this optical precision. In other words, the imaging quality. And the wavelength coverage out in space before. We've had the Hubble, which had got image quality, but not the wavelength coverage. We've had things like the Herschel mission and so on, which had the infrared capability, but not the image quality or the collecting area. So it builds on other things, but it really is something fantastic and new. Okay, well, what I suggest we do, can we have the first slide? Okay.
Wasn't quite the most dramatic reveal we had yesterday on the NASA live stream, was it?
Right. So we'll start where we start. And so Steve will have to wait for a while before he starts slobbering about the wonderful image. Who wants to talk about this one?
I think it should be exoplanets on the end, shouldn't it?
That should be me. Just take it off now. Yeah, so Stephen actually arranged the pictures in distance, so that's why the exoplanet, I guess, is first. And yeah, so first maybe start with what we're actually seeing in the exoplanet spectrum that was released yesterday. And Stephen very helpfully put up the actual light curve. So we look at actually like a transit of an exoplanet. So the exoplanet goes in front of its host star, blocking the light of the star, and produces this light curve. So this dip in the light, and that's what we're observing. But then we don't only observe it in one wavelength, but we observe it in in the whole wavelength range, basically. So we produce a spectrum. And we have like multiple of these light curves that we fit then and look at how this like transit depth changes in wavelength, which is basically that you can see it as kind of like the atmosphere around the planet up there. So if there's something in the atmosphere there that absorbs the light, then the exoplanet looks bigger than it is, like the absorber blocks the light. So we have a change at like an absorption feature. And that's, if you click to the next slide, is what we're seeing here. So if we have the water feature, basically absorbs the light, and we can see it in the transmission spectrum there.
Okay, now, how many other planets have we exoplanets have we actually got water vapor on? Is it many or?
Quite a few.
Quite a few.
Quite a few.
But presumably why is this important? Because it means that this shows that we're going to see a lot more with this device.
Yes, and also if you compare it to the Hubble Space Telescope, I presume, I suspect that's why they chose this instrument for the first transmission spectrum, is that NIRIS also covers the like a part of the wavelength range that Hubble also covers. So you can directly compare the precision between Hubble and the JWST. And like, I have a laser pointer now, fancy. So instead of like the hundreds of parts per million, the precision that Hubble has, the JWST has done like only the order of the tens. So we can really like narrow it down and not just get the abundance like way better, like how much water is in the atmosphere, but we can also probe for other elements and not just water that are not visible in the HST coverage. When I say HST, it's the Hubble Space Telescope. I should probably add to that.
Okay, thank you. Would any other panel member like to add anything?
Yeah, I mean, I'd love to tell a story about yesterday when we first saw this spectrum. So there was a load of what we call parallel sessions going on. So we'd all sort of separated off into like the galaxy experts go over here and the planet experts go over here. And we sort of paused our science to watch the NASA live stream and watch this image come through. And I was sat in a room full of other galaxy experts. And this spectra came on the screen and we all went, ooh, we have no idea what we're looking at because we literally had no idea. But the funny thing is, can we get the spectrum back on the screen?
It's on there.
Yeah, here we go. So what you're seeing here on the x-axis, on the horizontal axis there is the wavelength of light. So it's the type of light that we're getting. And then all the data points in the line is basically saying how much of that light is blocked. So when you see a bump, it says more light is blocked. But usually when we see these things, we're putting the amount of light detected. So if you have light blocked, you're used to seeing things going down on the spectrum. At least that's how we have it in galaxies anyway. I was expecting drops and gaps. So when I saw bumps, I was like, what? Like, what's going on? I thought there was water like emitting light in the atmosphere, but it was only when I saw, if you look at the vertical axis there, it says amount of light blocked, and then the penny dropped, and then all of us in the galaxy room went, oh, okay, we finally understand what this is. So if you were confused when you first saw this spectrum yesterday and didn't think it looked that spectacular, know that a room full of galaxy experts were also thinking the same thing as well.
And me too. Okay, can I ask, is there anybody in the audience who'd like to ask a question at all about this spectrum or the prospects for the future? One there, if we can get a microphone in there.
I'm quite new to spectra, and one of the things that's really obvious in looking at the spectrograph we have there is that the data fits quite closely in the lower wavelengths, and then towards the end doesn't. Why is that?
Okay, so one thing I have to add here is that this data reduction has been done fairly quickly, and there's a lot of work that goes behind actually getting to the spectrum, is because you have to fit these light curves for each individual wavelength bin, and you have to extract the spectrum. And NIRIS is really hard. They've actually put out the NIRIS spectrum now, and it kind of spreads out the spectrum. But you have multiple orders overlapping, so it's really hard to actually get that. So there might be a lot of systematics and noise still in there that it needs to take time until we learn what's happening there and to actually get them narrowed down. So that's probably what's happening in the lower wavelength range and in the higher ones as well, that we don't understand what's happening there yet.
Well spotted. They need to do their homework harder. Any other questions before we move on to a different slide? Anyone online? No? Yes, there's a question there.
It's more a question about the future. I mean, we're very keen to see missions on exoplanets from the UK. We've got Ariel coming up. Is that the sort of quality of information we can expect from Ariel, or will we get much better information in the future? And this is just a taster.
Okay, Ariel is a bit of the part of the mission of Ariel is more getting a lot of spectrum quickly, with a lot of exoplanets. I think they have I don't know, hundreds. I think they want to get in a couple of years. Please correct me if any Ariel people are in the audience. And JWST is more looking into specific planets for a longer amount of time, and also the wavelength coverage is different. So they're more complementary than challenging or competitive. So I think Ariel is going to add a lot of information there. So, and I think to fully understand an exoplanet spectrum, you also need the whole wavelength coverage. For this, the wiggles in the of the water and stuff, we only can really narrow down that if we have optical spectrum as well, and we need to get a whole full wavelength range to really understand an exoplanet spectrum.
Because that spectrum that we showed is what fraction of the whole spectrum roughly that JWST will be able to get?
That was from 1 to 5 micron, I want to say. Well, it's
Can we look at it again? There we are. What's it?
Oh,
No, it's 0.75 to...
So 10%.
Yeah, about 10%. So you get 10 times more for your money.
Can I also add an anecdote? I was working on shift in mission control on the very first day we got MIRI transiting spectroscopy of exoplanets. So the day before, we were a bit anxious about getting the timing right for when the transit was happening, because everything is loaded onto the schedule 24 hours in advance at that stage, and we weren't entirely sure about the precise timing of the transit. So the next day we started my shift and we're thinking, oh, is this observation going to start on time or not start on time? And so there's a bit of anxiety with that going on, to making sure we did get the full transit to calibrate this, because this is the first time MIRI instrument was doing this observation. And I know some of the other instruments were doing this, and their first transit events failed just because they got the timings wrong. Anyway, the transit happened. It was not quite perfect timing, but not far off. And then later on in the shift, we were frantically downloading on the archive to see when the data was brought down from the telescope, and just on the fly processing through the pipeline. And you could see just in the raw data, just without doing any processing, the actual transit. And that was stunning. The fact that we didn't have to do anything, you could see really clearly the transit right there and then. So in the space of an 8-hour shift, we'd taken the first transit, we'd gone through the pipeline and seen the dip in the white light spectra. And then that was cleaned up by a colleague in the next 20 minutes, and you could really clearly see it. So I think the lesson from that is it's very well calibrated, and you're not going to do much processing. But that was one of my favourite shifts.
That's so exciting. It puts me in mind of Galileo, putting his, good God, Jupiter's got something going around it, and it's the same sort of real time. Wonderful.
Have you just given us some insider info there? Because that's a nearest spectrum, not a MIRI spectrum.
Yeah. The data's, it's 12th, it's past
It's public now?
It's public
Oh,
now.
I'm getting my hands on that.
I thought it's coming out tomorrow.
Yeah, but
commissioning.
I can talk about commissioning now.
Yeah.
Because we've had, I was under embargo. I couldn't say anything until,
Right, sign this.
until yesterday.
Okay, let's move on to the next slide, if we might. Now, who's going to talk about this?
It's got to be Olivia,
I think that's me.
Right, off you go.
This is absolutely stunning. Beyond stunning. I'm amazed that we're looking at star formation in the Carina Nebula, and this just shows the dynamic range of Webb. I was worried at any star formation nearby we were going to saturate. So these observations are obvious. I don't know, I haven't downloaded the files yet. My computer's tricking away downloading this, but I imagine these are very short observations. This is with NIRCam. Yes, this is just the NIRCam one.
Might have the other one as well.
Oh, you might have the other one as well. Oh,
go.
beautiful. NIRCam and MIRI, my favourite. And I'm also very excited because in 3 days, I'm getting most of these filters on a star formation region in a nearby galaxy in all these wavelengths. So I'm very excited to be able to do this. Anyway, if we go back to the NIRCam, because I think this just blew me away. Absolutely blew me away. You can see here, you can see all these regions, these bubbles. If you look at the Hubble picture of this galaxy, those bubbles are not there, it's dust. You can't see through those regions. And if you just do a GIF of flipping between the two, it's like peeling back an onion and you can see into the site of star formation. But what really excites me about this is you have all these really red objects now. These are missing from the Hubble data, but are present in the NIRCam data. And these are on these dust ridges. And this really blew me away.
You've got so excited. You're pushing this in another galaxy. You mentioned this is in our own galaxy.
This is in our own galaxy.
Yeah.
I'm looking at it in the Magellanic Clouds in 3 days' time. And then we're going out to do this as far as 18 megaparsecs away.
So there'll be other regions like this, but in other galaxies.
Yes.
Yeah. Okay.
And I think also Orion's being observed as part of Cycle 1 as well, which is also extremely bright. So, but you can do it in Carina, you can do it here. And if you look carefully, I think, can you go to the MIRI image, please? Here, you have a jet an outflow of a jet from a young star in the process of formation. And just, that's magical. This in such a short amount of time. And all the dust. Yeah, I could talk about this for a very long time, so I should probably let people talk.
Anybody else on the panel want to say anything?
I just want to ask Libby, do you have any insight into why Carina was picked over any other target, like Orion, for example? Because I feel like Orion it made the most sense to me, or even like Eagle Nebula, Pillars of Creation, so iconic of a Hubble image.
A lot of, I think, nearby star formation regions are just so bright. They will saturate. So I was really surprised to see this on the list of early release observations because I thought we would be saturating. Orion is a risk, I think. But they're being very careful about how to take those observations. So yeah, I really wasn't expecting to see anything in the nearby galaxy. Though I talked to Klaus Pontoppidan, he was actually the guy who was in charge of all the ERO observations, the first person to see every single one of them. And his rule of thumb was, if it doesn't saturate in Spitzer, yay Spitzer, in the interstellar structure, it's not going to saturate in Webb. So that's what his rule of thumb is. So look out for all your star formation regions in our own galaxy that don't saturate in Spitzer, and you can do it.
Any questions from the audience who'd like to ask about this image or the related physics? Or is there's one up the back, up there?
As well.
Just while you're running up there, I guess we got really lucky with this object because only a small fraction of the sky is visible at any one time to Webb, unlike Hubble. So this must just been a fortuitous that we had it within that period.
There was 90 objects in the ERO list that they had proposed.
Okay.
They narrowed that down, so once they knew when the launch date was, they could then pick what objects they were going to put into this 2-week window. So I was on shift as well when a lot of the EROs were being taken, and the science lead was asking me questions, and I didn't know because it was kept secret from all of us until yesterday. So even if it was working on our own instruments, we could see the integrations going up, but we had no idea where it was pointing or what was going on. And if there was a problem, we had to basically wake the two people up who knew.
Right. Okay. At the back.
Hi, I've just got a question about the MIRI image, I think. The coloured image, not grayscale.
Can we have that back again? There we are. Not that one, the other one.
Yeah.
Oh, that's not grayscale, that's colour.
Oh, I've just...
There's some fantastic colour in there. You just need to look properly.
The other image you wanted?
So this was.
That's the near cam and MIRI.
Yeah.
Oh, no.
So this is the MIRI and NIRCam, right?
Yeah,
Yes.
that's confident.
Which one did you want?
The previous one.
The NIRCam one.
The
Yeah.
That one. Yeah.
So looking at this, there's almost a bluish haze like rising up above the stuff, like the gas cloud or the dust, sorry. And there's almost like fringes that you can see, like bright fringes in that blue haze. Is there any comments about what that could be?
I'm not sure what that is. I was puzzling over that yesterday, and I want to actually look at the FITS files to see what's going on there. I think, yeah, there's all sorts of things could be going on physics-wise. I'm wondering if it falls into the cloud, but I don't know.
I read on the NASA site that it's hot ionized gas that's evaporating essentially almost. That's
Okay,
being sort of
fantastic.
streaming off. From
Isn't it? Is it reflection nebulae or is it glowing in its own? I wonder if it's a bit reflection nebulae, but it presumably could be glowing in its own right.
You're talking about the haze on the sort of, if we think of this as a mountain range, you're talking about the, like sort of that rising off the top. Yeah. That's essentially what they said it was hot ionized gas streaming off the nebula essentially that's been heated up by all the ultraviolet radiation from the protostars.
So I can't actually see what the number is here. I can't read that, but that would give us an idea.
0.9 microns. Oh, I don't work in, not microns, infrared astronomer.
9,000 angstroms.
Okay, so is that the 0900W?
Yes.
Oh, okay. Yeah, so that will be, the ionized gas just glowing, I think. Thought we've seen that.
Okay. Any other questions?
One over here.
Was there one? There we are.
Must also say that although I'm a galaxy astrophysicist, this was my favorite image by far. It's just amazing. And the screen really doesn't do it any credit. You need to download the actual image and zoom in.
You just said the deep field was your favorite image. You got to pick one, Steve. You got to pick.
Favorite scientifically, not aesthetically.
Oh, come on! At Christmas, do you say that's my favourite toy? No, that's my favourite.
They're all my favorite.
Yeah. This one here.
Yeah, really basic question, but just out of interest, what kind of sky coverage are we looking at on this image?
Anyone have any idea of scale?
What the angular field is?
Is it in the handy book? I'm not sure which part of the module it has observed with. You can.
It says 2 light years there. Look.
Yeah.
Yes.
Oh, but in terms of like sky size,
Yeah, like
Carina Nebula would be a few arc seconds across.
Yes.
Yeah.
It depends
Well,
on.
no,
There's
it's-
many modules you can use
It must be-
with NIRCam, so I don't know exactly until I've got the FITS files downloaded how big that is and what part they've used.
Well, the star images must be of order two. Well, no, they mustn't be in space. At the order of the resolution limit. So yes, a few minutes.
I don't know which one. Small, I mean, the nebula itself, the whole nebula itself, maybe, but I imagine they've just picked a smaller region.
So this might be half a minute or.
Does anyone in the audience know?
Look, somebody look it up
There's
quickly.
a few people with purple lanyards.
Anybody know?
Someone-
2 by 2 arc minutes. That would sound reasonable as an astrophysical estimate.
So if that's the case, this image actually extends much further. So the footprint of NIRCam is 8 by 4 arc minutes, something like that. So there might actually be a lot more data out there.
I suspect this is just one tile of a NIRCam data cube, not data cube, but the field view footprint. There's 2 cameras operating with NIRCam, so just in case of redundancies. So you actually get quite a large sky coverage, but there's lots of gaps. And because there's no gaps in this, and these were taken very quickly, I suspect it's just a very small quadrant of one of the images.
Okay, well, let's move on to the next one, see what's in the pack.
Spoiler before.
Oh, I think this one's mine as well. Evolved stars, yay, lovely. Planetary nebula, even better. I clapped when I saw the MIRI version of this. This is, again, stunning. Dying stars, planetary nebulae. What you can really see here in the center. Do you have the MIRI version?
Maybe.
Oh, no, we don't have the MIRI version.
Oh.
So what we saw here in the center in the MIRI version was the binary star companion to this. And that was a new discovery, brand new discovery for this planetary nebula. Again, I saw this on the list of targets and thought, oh, there's other very pretty planetary nebulae we observed during commissioning. Why have they picked this? Again, hint, look at the archive tomorrow. There's a lot of planetary nebulae out there that were observed, the good calibration sources. But this is fantastic. This is a dying star. So in the center, there is a hot white dwarf. Okay, there's a hot white dwarf in the center. In the MIRI, that's red, and so there's some dust there as well. And then there's this wind of the shell of the dust that's been blown away, and it's traveling at around 8 miles per second. This slow wind from this planetary nebula. I think this is just marvelous. Again, the asymmetric shape is due to a binary companion. That's why we knew it was a binary, but we hadn't seen it. And just everything about this, I just love, again, if you get this onto your computer, all these dust lanes, just the absolute contrast between the dust, beautiful. And it's going to make modeling this in the future a pain. I'm looking forward to it.
So presumably it's the binary nature gives an asymmetric wind, and hence you get the strange shape.
So in this field of astronomy, we assume the previous stage of evolution, the ADUE stage, is all single stars. And then as soon as you get to planetary nebula, the next stage in their evolution, they're all binaries. So we need to work on models a bit better as well.
That's interesting.
But I love this. And so this is a friend of mine, Carl, who was in charge of processing this image. You may have seen him yesterday. I've known him for a decade. And he actually made me grab a picture of the different MIRI filters, because apart from this bet of this background galaxy / planetary nebula structure, to see if it was, because I convolved a lot of these filters to see what they would look like, and this was part of the analysis. But he didn't tell me this. He just said, oh, that figure's interesting. Let's have a look a bit more. But anyway, I'm really excited by this and the others in the archive. I think you can tell I'm excited by
Anybody
everything.
else on the panel want to say anything more about this one?
I mean, planetary nebula aside, the most amazing thing for me is the amount of background galaxies you still get, even focusing on the nebula. It's incredible. You could probably do some galaxy science on. There's 3 just in the top left corner near that edge on one that you were just talking about, Libby, right? There's sort of one to the right and then one sort of below it on the left as well that are beautiful spiral shapes. I don't feel like there's going to be any more blank space or empty sky with Webb. I think everything you pointed out, we're going to get stuff in the background that's going to be serendipitous or, sort of bonus science that we can do, which is fab to think.
Yeah. Okay. Questions from the audience about this one? Here.
Hello, sorry, I was just wondering about these dust lines that we can see almost in lines and waves around. Are those also present spherically all around, like even in front of us as well? And if so, why can't we see them face on?
I think it's due to the structure. I was pondering this yesterday, actually. If you look through here, you can see some red dust on the other side. So I'm just wondering, have we seen through the first layer are we seeing the center, and then there's actually dust on the other side as well? I haven't had a chance to really think about this as much, but I would like to think about this some more. But I suspect it's all.
Is it like a bubble? You look at a soap bubble, you see through the middle of the soap bubble, but the edges you've got a higher optical depth, so you see the edge more than you do the
Same as
center.
like air mass in the atmosphere as well, in that kind of thing. When you look there at the zenith, you're looking through less air mass, so it's much thinner than at the horizon.
Thank you.
Any other questions about this? Up the back there. Sorry about this. Somebody's going to have to run. You're supposed to wave.
Yeah. I'm just wondering what sort of exposure times JWST used to get that much detail, because I imagine there's not a lot of light coming from it.
The 5 images you've seen were taken in 4 days of observing.
Right. Okay. Thank you.
So use that.
There you go. Easy question.
Okay. Any online questions? Just to check whoever's checking. Any online questions that I should know about?
There's also one.
Yep, there's one.
Maybe want to point out quickly here that
Don't move your
exoplanet is not
laptop.
exposure time.
Sorry, Karen.
No, I just wanted to point out that exoplanet is a bit different because you have time series observations. So you don't take a single picture, you take multiple ones over the whole time, right? So we want to capture transit. takes a bit longer then.
Okay, online question?
Yes, there was one that came online, which was talking about that dust through the middle. And it says there's dust going through the middle of the blue bit from 8 o'clock to 2 o'clock, just on the right of what I assume is the white dwarf star. What is the dust doing there? And is it newer than the other dust? So like a follow-up to your previous comment.
I suspect it was emitted all at the same time. Well, I say all at the same time. I think the fact that we're seeing these ridges in the dust implies it wasn't all at the same time. But I think in astronomy terms, you can say more or less. But I think there's just a lot of science we can do on just this data.
Yeah. Would have been puffed out and forming and instabilities and.
Oh, I don't think you want to get me started on dust physics. But yeah, there's a lot of interesting complex processes and going on.
Right. Okay, good. Any further questions on this image? Yeah, there's somebody there.
Thank you. You mentioned slow stellar winds. I just wondered if you had any estimates of the velocity of these stellar winds?
Normally, we just assume 10 kilometers per second was the default value in all the models. I think we'll have to move away from that now.
What do you reckon for this?
Well, apparently, according to the press release, it was 8 miles per second, this wind. I don't know what that is in proper units.
Thank you.
Okay. Shall we move on then to the next image? Yes, let's move on to the next image.
No, it's my baby.
Now this is Stefan's Quintet, which I always think it sounds like Stefan Grappelli playing in the Club de Paris. But I believe this was first, this group of galaxies was first discovered in 1877 by Edouard Stefan at Marseille. So that's where the name comes from.
Oh, I didn't know it was a last name. I assumed it was a first name.
No, it's his last name. And perhaps you can tell us about this, because this is a well-known object by those who know it well.
Yes.
And in the past, has been a very controversial object for reasons which are now settled. But perhaps you can go into that.
Yeah, so this is a collection of 5 galaxies. It's what's known as a very compact group of galaxies. So we see galaxies grouped together everywhere in the universe, but these are much more tightly grouped than we normally see. 4 of them are interacting together, and 1 of them is not. And I'm sure you can pick out that sort of lone wolf at the bottom there that seems to be left by itself. And that was why it was necessarily slightly controversial, because we didn't know which ones are involved in the interaction. But Webb has essentially revealed that interaction taking place. So what you're seeing is a near cam image, so the near infrared close to visible wavelengths that we use to see through the dust. And then you're seeing the MIRI wavelengths also overlaid on that as well. So those are the sort of the orangey regions that you can see in here. And that's essentially the wavelengths we use to see the emission from the dust itself. The dust starts to glow at some point.
Can I just clarify here? Because I should have got a picture out and had a good look at this beforehand. But of these galaxies, 4 of them are close together?
Yes. So
That's
1, 2, 3, 4.
And the one that's
This
much
one.
closer to us, is that right? That's much closer to
I'm
us.
not sure how have we got redshifts on that. But
It's the spiral that's the one closest to us.
this one?
This one.
Yeah, I think they're all in a group. I think they're all at similar distances, but this one's.
No,
that's the
one of them.
foreground one.
No,
Oh,
there
is
a
that foreground?
That's the
one,
foreground one.
Great.
which is about, I think, 1/7 of the distance away.
Sure. Okay. Cool.
So, and of course, in the past, that in the great redshift debate of the past, this was pulled up and said, oh, redshifts can't be cosmological, because look at this lot, they're all at the same distance but different redshifts. But obviously, we know now that's a foreground galaxy. But the interesting stuff, which you're going to tell us about, is in the background there.
Yes, exactly. So we can see the different emissions. You can see through the dust, and you can see the dust itself as well. So with these galaxies that are interacting, you can see this sort of like big chain that's come off these 2, and also this one here as well. But you can also see these tendrils. This is what we dub affectionately as jellyfish galaxies. If they're being sort of like stripped away in an interaction, it forms that sort of jelly shape. And you can really see the dust that's being drawn off as well, that's glowing from that too, which I think is fantastic. In this galaxy, I don't know if we can zoom into it, whoever's in control of the slides, if we can zoom into that foreground galaxy that is quite close. The thing that blew my mind the most was that they were like, oh, we've resolved individual stars in this galaxy, which is I don't know if anyone, you must have reacted to that as well. I just thought that's absolutely insane. We
I
can
did.
just about do that with Andromeda, with the Hubble Space Telescope, but you know, it's very, very difficult. The fact that it's done that for this galaxy at such a great distance is amazing. Have we got just the MIRI image of this as well? Yeah, this one. So first of all, the structure of the dust in this one is incredible. Like it's not arranged like a normal spiral. It's what we call a flocculent spiral galaxy. Flocculent, I think, is it Latin or Greek? I'm not sure, but it means fluffy, because essentially you can't, if you tried to decide how many spiral arms are in that thing, you couldn't. You'd be there counting probably past 100. You can obviously see the dust here glowing much more brightly as well in the different wavelengths. Obviously, it's slightly different temperatures. The best thing in this entire image was this bright point up here that they picked out with the MIRI image. It's incredibly bright, so much that it looks like a star. It's got that classic 8-point diffraction spike shape that we're going to become very familiar with JWST images because of the way that the light travels through the hexagon-shaped optics of the telescope. You get that shape. And essentially it tells you there's something incredibly, incredibly bright in the very center of that galaxy that's glowing in the mid-infrared. And essentially what that is hydrogen gas spiraling around the supermassive black hole in the center that's been accelerated to huge speeds so much that it starts to glow so that we can see it, which I think is incredible. And yeah, then they did this as well. This, oh my God, right. I saw this. I was like, what? So this is what's known as, so MIRI is, and correct me guys who did all the engineering and everything on it, it's called an IFU. So essentially what it does is it takes a spectrum at every pixel, which means you also get an image at every single wavelength. So the wavelength that we know that different molecules emit light at, you can say, okay, what does that galaxy look like at this wavelength? So you can say, okay, where is the hydrogen? Where is the oxygen? And so that's what they've done here. And so you can see, okay, this is where the atomic hydrogen is. So atomic hydrogen just being one singular atom of hydrogen. But then here's where the molecular hydrogen is, which is, two hydrogens bonded together. And you can see this ring in the very center of the galaxy of molecular hydrogen, which is clearly the hydrogen sort of, spiraling around the middle that's going to feed that accretion disk around the supermassive black hole, which was just, it's insane to see. I'm so obsessed with the Event Horizon Telescope images, which are big orange donuts, and now we've got a little red donut as well. So it's really, really nice to see.
Okay, great. Piyal, can I ask you, you helped
Yeah.
build this.
Definitely helped.
You didn't do it on your own, I understand that. And how do you feel, seeing these images? And are they better than you'd hoped they'd been? Or
Oh, absolutely. Like, it just beggars belief to see this. We worked so hard and so long, and certainly from a management point of view, there was real push to try and, because the project was slipping on schedule and cost, was to try and de-scope, try to get things put time ahead. But the management were really strong on trying to make sure we did things properly and correctly. We really did risk mitigate, make sure there was margin in there. I think the spacecraft team as well, we knew that we were being so ambitious. This observatory looks like nothing else. We're doing things that have never been done before, and it does take time, unfortunately. But all of that means that it pays back dividends, and it just feels like relief that it actually has paid off. Because across the whole project, we were really pushing the boundaries here. Like, MIRI is cooled down to 6 degrees above absolute zero, but it's built in ambient room conditions and aligned at ambient room conditions. So it goes through a massive shift in how it behaves, how it operates, as it shrinks, physically shrinks, massively shrinks down, and gets itself into that condition set. And then to do that, and then shift it off to, such a far distance away, and make it operate autonomously.
1.5 million miles, or 1.5 million kilometers, I think it is.
Exactly, yeah. And they expect that to be autonomous and with all the risk and everything like that, and then see this, it's just, wow, it's just fantastic.
I think there was something, was 100, I can't remember the number of single point possible.
283.
How many?
283.
No
That
wonder
number's
you're
burnt in my brain.
relieved. 283 single
Single point failures,
possible failures. So it's tremendous, and it is extraordinary that it worked. Okay, let's go back to the picture again.
I actually have another question for you, because I mean, I can describe it so simply as how it takes a spectrum at every pixel. And I don't know if any of you have seen the videos that NASA put together of just the light path through these instruments. Just it comes in, it bounces off this mirror, it bounces off this mirror, it bounces off this mirror, it goes through this instrument, it goes through this instrument, it bounces off this mirror, it bounces. Like, how do you design something like that has so many steps in it? Like, how do you start?
That's a really good question. Every single mirror is so precisely aligned, and you basically pin the mirrors in position very, very precisely. And each one of those holes that basically governs the alignment, when you're drilling them, if there's something like a couple of degrees C temperature change in the material during that process, you basically lost alignment. And then you think about how many mirrors, there's hundreds of mirrors in there, and they all have to be precisely aligned. And then on top of that, you then have to cool it down so they all shrink and have to maintain that alignment across there. So MIRI itself, we overcame that by MIRI being predominantly just made out of aluminium. It's almost entirely aluminium. So all the materials don't fight against each other, all the bits, and moves uniformly. So yeah.
Like, how do you decide how many? Like, why is there so many mirrors? Like you'd think that would be so lossy every time it bounced off it. So what is the point of the?
It's the genius of the it's the optical design at the Astronomy Technology Centre in Edinburgh. They put that through, but it has to split out those wavelengths of light in order to get that. It has to go through all those steps of splitting. So you get the good stuff at the detector, and yes, it has to be done.
Yeah, you'll always reduce to the minimum the number of reflections you can, but you can't get rid of them all, so you're constrained with that. Okay, let's just go back to the picture again. Can we go back to the main picture? That one will do, or that one. Anybody want to add anything more about that?
Can I add two things to this? There is, can I have the pen? So before, how you were saying, oh, I really like the galaxies in those images. I'm going to say the opposite, and I'm going to say I really like the stars in these images. And a few people in the audience who are interested in dusty stars. These green blobs here are bright at 10 microns, and they are stars at 10 microns. They are silicate, they're dusty stars. So not only have we detected the stars at the shorter wavelengths where we've got the best resolution, at the longer wavelength PSFs and MIRI, we're also detecting stars this far away, and this blew me away. So that's one thing. And the other thing, actually, it's no longer a 5 system. I think there's another galaxy in here of PAHs that's bright in green. So there may be another galaxy right there as well.
Orbiting that?
I don't know. I don't know. I'm not a galaxy person. I look at the stuff in the galaxies, but this green blob here, I think if you look at it, I think it's got spiral arms. If you're looking in closer, so I think there's another galaxy there.
Okay.
I think the question has been, is it at the same redshift as the big one? If so, what's the velocity of it? In terms of line of sight.
The redshift of Stefan's quintet.
Exactly. Yeah. So there's lots of questions to ask.
Don't answer a question on that until it's been measured.
May I also say one final thing? I think one of the fantastic things about the engineering, just to comment on the engineering, the reason why we've got a 20-year mission is because the engineering was so fantastic. The launch was amazing as well, and that was a good part of it, but the mass budget and the careful engineering precision that they did. And so I just want to say thank you. And yes, as a scientist, I really appreciate this. Just keeping everything on spec and to such high quality has given me a 20-year plus lifetime. So thank you.
Amazing. But I have to say the team across the board, they preserved a huge amount of margin to try and compensate for any uncertainty. We knew that when we were challenged and things were hard to build the instrument, there was always that kind of thing, well, are we just over designing this? And you try and question the requirements. And everyone really did stay really true to those requirements. And that's what's allowed us to contain those margins. That means that the actual spacecraft actually exceeds what we actually hoped it would do. Yeah. So it's really good.
Good. I also just say how special MIRI is, because it's very different from the other instruments, right? It operates at different wavelengths, it has to be cooled. But also MIRI doesn't just do spectroscopy we were talking about, it does spectroscopy, the integral field spectroscopy, and also imaging. And none of the other instruments do all of these things together. So it's really the unique instrument. And obviously we have to say this because we're in the UK, but it really is the most advanced. And I say that with a little bit of a heavy heart because it's actually the one instrument that I will probably never use for my own science.
I think we could convince you somehow.
I'll try. You give me enough data, I'll do it.
Any questions before we move on? Because we've got the best till last. So 2 quick ones here, just quick ones, please. Yes, the back one first, and then the...
Thank you. I'm just wondering, because I'm not familiar with infrared, but obviously you're color coding, and I'm guessing for brightness and temperature, does it go kind of red for cool, and then green, and then blue, and then white? And secondly, because you've got different cameras at different or different instruments at different wavelengths that they're looking at. Is there any correlation between something I see that's the same color in each in the different cameras, or are they completely effectively transcribed?
Who'd like to answer that?
I can answer that. So they're using the same color coding scales as they use for Hubble. So it's always from wavelength range. They tend to go for the shortest wavelength towards blue, and then move to longer wavelengths. I've noticed in some of these images, they may have mixed and matched a bit with, they've done that mostly for NIRCam and for MIRI individually, but in those combined images, you notice that the shortest wavelength MIRI is closer in color to the shortest wavelength NIRCam image.
And one here, or then we'll move on.
I guess as an amateur astronomer as well, I think many of us really appreciated that image amongst the five, because many of us have observed that ourselves with our own little telescopes in the back garden. It's also the combination that's used in It's a Wonderful Life, the film. So I guess the question really around that was, did the PR team pick that image to study, or was it a genuine science issue that led them to choose it? Is it the PR favorite image?
Oh, me again. Okay. Astronomers from around the world were asked for what would make stunning, the wow images to start off with. And that's where they gained that list of initial objects for. And then I think there was some questions then, how would it work in the, so then there's some science questions as well. It wasn't really science focused. It was mainly, will this look good? How do we really show off just the quick capabilities? So I think favorite objects.
And I think you're allowed that for the first 2 weeks in 20 years. Okay, let's move on to the final image, or final display of images, and to this favorite one. Steve, I can see you bristling and ready to explode. So before you go supernova, perhaps you'd like to say a bit about this image.
So what we're seeing here is Joe Biden's favorite image. So this is the one that he chose to release first to the world. So obviously that means it must be the best, no offense. It's actually not my favorite, as I said before, in terms of aesthetics. What we're seeing here is, Webb's first deep field. So this is a field of galaxies, but it's a special field of galaxies. So this is a huge collection of galaxies called a cluster of galaxies. And the reason why we look at these clusters of galaxies is actually most of the time, we don't really care about the cluster itself. We actually care about what the cluster is doing to the things behind the cluster. So these big clusters actually act as natural lenses in space. And they actually, via their gravity, and this is something that was predicted by Einstein 105 years ago or so, is actually because of their gravity, they actually magnify and boost the light from galaxies behind. And so what you see in this image, and I don't think I have a zoom in afterwards, but what we see in this image are these features over here, these kind of smeared out galaxies. And these are galaxies behind this cluster that have been, expanded, and we're actually magnifying them there. But what's really, really cool about this image is that it's a snapshot of almost the entire history of our universe. So because light takes a certain amount of time to travel across the universe, the further away we look, the further back in time we're looking. And it just so happens that images like this, these crowded fields of galaxies, they include galaxies, across the entire history. And so actually some of the little red blobs that we see in this image, we now know are galaxies that were present when the universe was only a tiny fraction of its current age. And so if we go to this next image, we actually see that we haven't just obtained an image, and this was the great surprise to us. We thought we were just going to get an image, but we also got spectroscopy from one of the other instruments. In fact, we got spectroscopy from 2 instruments, and we also got MIRI imaging as well. So we were really, really lucky here. That's because it's Joe Biden's favorite galaxy. Obviously, yeah, let's do it. He loves it. And so what we've actually found here is that, and this is just a small number of the galaxies that have been studied with the spectroscopy, but these are the ones that we're really seeing in the early universe. And I don't have a doubt actually that this has been quite conservative. I suspect strongly there are galaxies that they have spectra for, which probably place them even closer to the Big Bang than these ones, right? But maybe they're not quite as good signal to noise, so they didn't believe them with the kind of simple reduction we've done so far. So I imagine tomorrow there'll be something on the archive where astronomers go and put all their results, say, actually we found something redshift 13 from this. And in fact, me and my team, we were actually downloading these images just before I came to this meeting. So this, yeah, amazing. This is almost the entire history of the universe. So this is, the first parallel of Hubble's iconic ultra deep field. So really, really exciting.
I couldn't believe this when I saw that bottom spectrum, especially, is the most distant one they've put there, 13.1 billion light years of the light's taken to get to us. That looks better than like a Sloan spectra of a nearby galaxy that's taken from the ground. I was like, I would kill for that kind of spectra. And I look at things that are only, a few 100 million light years away, and that's, tens of billions. It's amazing.
Well, when I was a graduate student many years ago, there was, nobody would have believed you could have got a redshift or something beyond maybe a tenth or something like that. So you're talking, maybe, I'm certainly, probably a bit. I'm beyond one. Nobody'd ever get a redshift beyond one, ever, with photographic plates or anything. No, couldn't do it. So this is sort of way back. And this is, you say, redshift 13, 14, whatever it will be, and you're getting right back.
With Hubble, what's the maximum now? Like 9?
Yeah.
11.
Yeah, so we've got something 11, but
it gets,
that's one.
we should say it gets very much more difficult the further away you get. That's why. Anyway, let's go to the audience. Who wants to ask a question about this extraordinary image? Anybody want to ask a question or make a point about it? Or are you just too stunned?
What is the exposure time for that deep field image? Because they clearly haven't had that long since the commissioning. So what could they do in the future? Go even further?
So I think this one, and maybe Olivia can correct me, I think it was about 12 hours.
It's 12 hours, 2 hours per filter.
Yeah.
So if you decided to, which probably you will decide to, if you spent a month out of your year, or a month out of first 3 years, you could do 60 times that. Is that right?
So in fact, at Christmas time, a program that I'm heavily involved in, we're going to have something which is 10 times longer exposure than this. So this is, it's called NG Deep, so the next generation deep field. And this is, our super deep field. So that is, a good, close to 100 hours of observing this one little patch of sky. And that's really, really exciting. I mean, this was fantastic, but, 10 times more. And I think there are data that's coming out today and tomorrow, which is very similar to this, but, more sky. So the one problem with this is that it's just one bit of sky. What we really want is more sky to have more galaxies, find the rare things as well.
Stephen, is NG Deep going to be a cluster like this, or is it going to be, we don't know anything that's there, kind of a deep field like with Hubble?
Exactly that. So it's a we don't know what's there kind of deep field. So it's a blank deep field. And there are various reasons why you use clusters and various reasons why you want to just use a blank deep field. You want to do both, really, but the one that we're going to see at Christmas time is this blank deep field. I should also say, actually, the image that we were just showing is actually only half the image. There is another half of the image, which is, a little bit further away from the center of the cluster, which is essentially, another deep field that we've got. So that was only half the data. And so we were downloading this data just before and looking at this image that nobody had ever seen before as well. And that was just fantastic.
Yeah, because that's the beauty of Webb, is that, NearCam looks at this patch simultaneously while MIRI looks over here and NearSpec looks over here and NIRISS looks down here. So you focus on one thing with one instrument, but you get all this bonus data, including the second patch of NearCam, which is that backup imaging that you were talking before. And I just can't wait to I don't have this time in my day, but all I want to do is be like, okay, somebody's looked at the Southern Ring Nebula, fine, yeah, whatever, okay, cool. They've downloaded that and what is in all of the other stuff around here though, and just spend a whole day looking through it, but maybe one day.
May I ask a naive question, because I don't know anything really about lensed galaxies. How do you go about analysing that with all those, I think you get multiple galaxies, you see it more than once as well. Where do you even start?
With great difficulty. Okay. So you have to build up a model for the mass, the dark matter and the stars that are in all those cluster galaxies. Once you have that model, you can then work out at any point on the sky what the kind of magnification is, what the lensing is. But that model is really, really difficult to create. But with that model, you can then say, actually, that bit of the sky there, that galaxy has been magnified by a factor of 10, or even sometimes 100 times you get a magnification. But it is a really tricky, and this is one of the reasons why we don't just use these clusters. We also use the blind fields, because the blind fields are actually, a lot easier to analyze. Clusters are tricky. And, in the clusters, you've got all of the actual cluster galaxies that getting in the way of all the cool stuff behind. Because I'm very biased, I apologize if there's any cluster scientists in the audience. I'm sure you can do something with that.
It gets easier though if you have spectra, right? Because if you have spectra, then you can tell which galaxies are repeats. Like it's the same galaxy seen twice because it's bent around because the spectra are identical.
Yes.
So then that gets easier, which is again why Webb is so great, because you don't just get images, you get spectra.
And presumably you can very much improve the model if you know that this one, this one, this one, and this one are all the same image.
Exactly. So that's why we were so excited that we also had spectra from this field. We weren't really expecting that, because that allows us to build this really, very accurate lens model. But it gives us a lot more work to do to try and do that.
Well, splendid.
So exciting.
Can we get the image back up again? Because I just want to point out one of the lensed galaxies that's there. We can do it on this one. It's a bit small. Yeah. Okay, can I have the little thing? So we have nicknamed this guy up here. This one. We've nicknamed this one the Slug, and I really want it to catch on. So if we can call this the Slug Galaxy from now on, that would make me very happy. Thank you.
We need to call one of those new galaxies a Biden galaxy then for politics.
But that's a very dim one.
I think we were joking that when we had a catalogue of these galaxies, we're going to name them Biden 1 or Lotus 1 or something.
Let's be grateful for his real support, actually. We should be very grateful, actually, for his real support and interest in this.
The one line at the end to say thank you to ESA, the Canadian Space Agency.
Well, there we are. Politics. Right. More questions, and we're running rapidly out of time. So just a couple more questions, please.
Yeah, thank you. Can I ask a little something about the scheduling of how this works? Because clearly, I'm not sure whether you're using reaction wheels or fuel to point the thing, but there's clearly a slew time, and so you'll have a schedule where you look at things in an optimum way. But what also is the settling time once you've pointed? So what is the slew rate? What's the system for moving it? And how long do you have to wait for it to settle? Because it is a point and stare, isn't it, with the imaging integration that you've got to do?
Is this a me question?
Yeah, I think so.
Okay. Right. So normally in the proposal tool, they assume an average slew of 30 minutes. Slews can take a while, depending on, it can move 90 degrees quite easily, no problem. But I've seen slews of up to an hour and a bit, depending on how far away where you're moving your targets to. So on average, the slew is 30 minutes. There is a fantastic paper on the archive today by Rigby et al. And there's many et al. There's over 500 co-authors, of which I think I'm one of them. It's actually not published yet. It's just on the archive. I think they don't know which journal it should go to, of all the actual set, including a very nice few pages on settling time. I have to say, I was so excited to read this 60-page document. I glossed over the exact numbers in there, but it's in the archive. You can look at it. It will tell you the exact number of how settled it is. It's not as long as you would expect. It's a lot of filter work. There's 5, I think there's 5 mechanical parts that control the telescope in general, and then the fuel for station keeping every so often. So far there's been 3 station keeping activities that uses fuel and consumables, and they skipped a few because they didn't need to use it yet. So I think that makes an even longer life.
Quickly again, it's a supplementary.
So just a quick follow on, you were saying earlier about a remarkable 20 years, which is fantastic. But is that limited by slew fuel, or is it cooling? That's coolant that's the problem there.
Coolant does not run out. MIRI has been engineered. MIRI is the only one that really needs coolant. Everything is passively cooled, but the coolant is in a closed loop cryocooler. Fantastic new piece of technology.
No, exactly. When I started, they were actually the cooler wasn't there. They hadn't invented it yet, and they had a big dewar, a big bottle of liquid nitrogen that would boil off. So that was really limited life for MIRI, and then. But luckily, they realized that liquid nitrogen would run out quite quickly and weighed quite a lot. And JPL pulled it out of the bag to get this new cooler design and bring it up to, with Northrop Grumman and other involvement, they got this cooler technology and said, yeah, we think we can work. But the cooler was a really big risk because it spans 7 different areas of spacecraft. It goes all the way from the 6 degrees Kelvin all the way up to the hottest part of spacecraft there. So all that chain has to work perfectly. So it's a real technical achievement there that they managed to pull off.
And presumably also another good for our political masters, if you want, an example of pure research driving a technological invention,
Exactly.
which is really impressive. Okay, one more question. Anybody want to ask? the privilege of asking the right. Yes, and bad luck, it's right up the back. Up in the corner.
Hi, thank you for this discussion. So I'm just curious about the deep field image. You mentioned that a lot of the image arcs are due to the lensing of background galaxies. Are there any examples of arcs that have been seen in this image that weren't seen by Hubble?
Oh, loads and loads of them. So we do have a Hubble image of this cluster, and it was, one of the deepest Hubble images taken by a program called RELIX. But if you just compare the two, there are loads missing. There's one really, really bright one. I don't know if we can come up with the image again. It might be quite difficult to see, but it's a really bright one, and it's really kind of mysteriously completely missing in the Hubble imaging, right? And this tells us that it's either something really unusual or it's something really, really far away. And I think that's one of the ones that we're, my team will be looking at right now while we're in this meeting to see if we can figure out what it is. Is it something that's, really weird and unusual, or is it something that's really, really far away? But there were a whole slew of those. Last night, we were just, dissecting this image and just picking out different ones and just saying, that one looks interesting, we should look at that later. So we were just going through this all through the night.
Yeah. So there's going to be slugs, snails, puppy dogs' tails. Yeah. Wonderful. Okay. I think that just about brings us to time. And I'd like to thank everybody for coming. I assume it's about time to wrap up, whoever's organising, presumably. Everybody's looking tired anyway. We're all excited out, overtired. Overwhelmed and overtired. So can I ask you to thank very much the panel for their expert comment on what's gone on. And I suppose we ought to just, as everybody's doing, congratulate everybody on the extraordinary success of this so far, of this mission, and with the amount of effort that's been put in and providing us with what is such a golden opportunity for what hopes to be the next 20 years. Thank you.